Here are solutions to some physics problems from Chapter 13, numbers 57, 72, 85, and 93. Number 57, this is the binary star system problem. Might have talked about this with some of you, but here's another look at it. So we've got two stars. Each of them has the mass of the Sun. They're one atomic unit apart, and they rotate around their center of mass, which is right here. Just to recap here, I think what we've already talked about in class, you cannot just drop Kepler's third law onto this situation, because Kepler's third law, we derived that based on the assumption that one object was rotating around the other one, and that assumes that one of them has a much smaller mass than the other, and these two have equal mass. So we're doing the same thing. We're starting at the same place, that the universal gravitational force is the thing that's causing that unbalanced force toward the center. In other words, that G, M, M, they're the same mass. I'm going to use that big M there, over R squared is equal to mv squared over R. The problem here is, and the reason that this is not just Kepler's third law, is that these R's are not the same. The universal gravitational force that one object feels because of the presence of another one depends on the distance between them. So this R here is the full radius, the distance between here and here. So that's one atomic unit. Sorry, not atomic unit, astronomical unit. And this R here, this is mv squared over R for something moving in a circle. So this R is 1/2 of an astronomical unit. You could go ahead and start plugging numbers in here, but it might be kind of fun to play with this and get a general expression here. So one of the m's cancels, and let's see what we have from there. That would give us gm over, I'm going to leave that as AU, astronomical unit squared, and then this one would multiply up to the other half, and I get 1/2 of an astronomical unit, and that would cancel out one of those. That's equal to v squared, so v would be the square root of this. And we also know that velocity of anything moving in a circle is 2 pi times the radius of the circle it's moving in, which is, once again, that's 1/2 an atomic unit, astronomical unit, just kidding, over the period. So squaring both sides of this equation, I get gm, I'm going to go ahead and drop that 2 down to the bottom, over 2 AUs is equal to 4 pi squared. I'm going to square that 1/2 and drop that to the bottom. That'd be 4t times an astronomical unit squared. So if I want to solve this for period, the period of our binary stars here is, moving that up here, I have the 4's cancel, I get 2 up there, so 2 pi squared, I've taken care of all the numerical constants, right, over gm times AU astronomical unit cubed. So it looks kind of like Kepler, but it's a 2 in there instead of a 4. And I think we can just go ahead and plug everything in now. Again, you could have done that with numbers along the way, but it's good practice to do that. So 2 pi squared over, I'm not sure that I have a g in here or not, so I'm going to go ahead and type it in, 6.67 times 10 to the negative 11th, and there's the mass the Sun, which is about 2 times 10 to the 30th kilograms, times astronomical unit cubed. An astronomical unit is about 1.5 times 10 to the 11th meters cubed. And that's giving me the period there. Oh, and I lost a t somewhere, didn't I? I feel like that should be a t squared. Where'd the other t go? Oh, I didn't square it here, did I? And that's a t squared. So that'd be the square root of that whole thing. The square root of my answer there. About 223. Let's see, that'd be 2.23 times 10 to the 7th seconds, I believe. 1, 2, 3, 4, 5, 6, 7. And then if I want to change that to years, I have to divide by 365 days. And divide by, in each day there's 86,400 seconds. That's about 0.71 years. Number 72. Typical neutron star might have a mass equal to that of the Sun, but a radius of only 10 kilometers. What's the gravitational acceleration at the surface of such a star? Well, the gravitational acceleration, universal gravitational force, is g m over r squared. So force equals mass times acceleration, which means mass times the gravity at the surface of that would be equal to g m over r squared, and the m's cancel out. So that's where our gravitational field strength, or acceleration due to gravity, that's where that comes from. It's the small m cancels. So for this neutron star, I have g times the mass of the Sun over the radius of this. If we're at the surface of it, it's only 10 kilometers, so that's 10,000 meters squared. Let me see if I have g stored in here. Nope. So 6.67 times 10 to the negative 11th. Store that as the letter g. And now if I type the letter g, there it is. So let's see, I've got g times the mass of the Sun, which is about 2 times 10 to the 30th, divided by 10,000 squared. So the acceleration due to gravity is about 1.3 times 10 to the 12th meters per second squared. That's some serious gravitational field strength right there. That's also newtons per kilogram, right? Same units. That's part A. Part B, how fast would an object be moving if it fell from rest through a distance of 1 meter? So that's a kinematics problem. So drop it from rest. We want to know how fast it would be going. We know that the acceleration is. And the delta y, it's falling 1 meter. I'm taking down to be the positive direction because it's only going down, so I'm making that and that both positive. So Vf squared is equal to Vi squared, which is 0, plus 2 times A times delta y. So I just need to take the square root of that. So this number times 2, and then the square root of that. So we'd be going about 1.6 times 10 to the 2, 3, 4, 5, 6 meters per second. Number 85. A projectile is fired vertically from Earth's surface with an initial speed of 10 kilometers per second. Neglecting air drag, how far above the surface of the Earth will it go? So this is an energy problem, going from here at the surface of the Earth to some highest point here. And here, it's got kinetic energy, and it's got universal gravitational potential, because it's an Earth radius from the center. That's 1/2 mv squared. That's negative gmm for r. And then when it gets up to here, that's the highest point, so it would have no kinetic energy, but it has universal gravitational potential, negative gmm over r. This is the radius of the Earth. This is the r here. And I'm just going to observe here that they are asking how far above the surface of the Earth will it go. So what I'm finding here, this r is from center to center. So when I find this, I'm going to have to subtract an Earth radius from that. No big deal. But they're looking for this distance, not the center to center. Okay, so conservation of energy, this has to be equal to this. So total mechanical energy, here's a high level version of that equation. So initially I have 1/2 m times v squared. That was, how fast was it going? 10 kilometers per second, so 10,000 meters per second squared minus g, the big M is the mass of the Earth, times little m over the radius of the Earth, equals negative g mass of the Earth, little m over the r that I'm looking for, well, almost the r that I'm looking for before I subtract the Earth radius out. All right, so let's put some more numbers in here. First of all, notice that the little m's cancel, which is good because I didn't know what that was. So I've got on this side 10,000 squared, half of that, so that's what? That's going to be 8 zeros. That's 5, 2, 3, 4, 5, 7 minus g times mass of the Earth over radius of the Earth. So let's see, g times the mass of the Earth is about 6 times 10 to the 24th. You might be using 5.97 or something there, but that should be close enough. Divided by the radius of the Earth, which is about 6.37 times 10 to the 6th. So it's at about 6.3 times 10 to the 1, 2, 3, 4, 5, 6, 7. So to the 7th. That's equal to negative gm over that r. G, and then the mass of the Earth again. That's about 4 times 10 to the 14th. So let's see if we can manage that. So here I've got 50 million rather. That's 5 times 10 to the 7th. You see that? Not that you need to see me drive my calculator. Minus 6.3 times 10 to the 7th. That's, I could have done that without a calculator, I suppose. Negative 1.3 times 10 to the 7th. Minus signs cancel, multiply that over to here, divide here. So we got 4 times 10 to the 14th divided by 1.3 times 10 to the 7th. And that's going to give me an R of about 3.1 times 10 to the 7th meters. And then subtract the radius of the Earth, which is about 6.4 times 10 to the 6th meters. And that gives me about 2.4 times 10 to the 7th meters. And let me just check my answer book here and make sure I have not led you astray here. And they have 2.5, so a little bit different rounding along the way, or different values for some of those, but that would certainly be acceptable. They also put it in kilometers. So there you go. There's that. If you're wondering, like, how do you know when you should add the radius of the Earth or subtract it or that sort of thing, you just have to make a good picture and trust that diagram and think about what you're looking for. I don't think any of these problems are well suited to just blindly plugging numbers in. Number 93, we've got planet Rotan with a mass of 7 times 10 to the 24th kilograms. So Earth is about 6 times 24, 10 to the 24th, so it's Earth-like. And a radius of 1,600 kilometers. Radius of Rotan, that would be 1.6 times 10 to the 1,600, so that would be 10 to the 6th meters. Gravitationally attracts a meteorite that's initially at rest relative to the planet at a distance great enough to take as infinite. And then the meteorite falls toward the planet. And we want to find the speed of the meteorite when it reaches the planet's surface. So this is another energy problem. We're just going the other way. So we're here, and we're going to get to here. So here, if the distance is taken to be infinite, that means, remember, by definition, that's where universal gravitational potential is equal to 0. And it's just barely getting nudged out of its location there toward this planet. So it starts with a kinetic energy also of 0. So then when it gets to the planet, it's going wicked fast, some 1/2 mv squared over r, and it also still has some universal gravitational potential, negative g, mass of Rotan, mass of the asteroid, meteorite rather, over r, and that's the r, that's the radius of the planet here. And we just need to solve for that v. So if this equals this, that means that negative g m over the radius of Rotan plus 1/2 mv squared is equal to 0. Small m's can cancel out from that. So it looks like we've got v is going to be equal to the square root of 2gm over the radius of Rotan. If you look at that and you're like, wait a second, that's the escape speed. Because this is the energy is conserved here, it should make sense that this is a reversible process. If you want to get something from here to infinity, well, the speed that is required to do that is going to be the exact same speed as if it goes from infinity back to here. Just like if you're rolling a cart up a track, and if you roll it up with some speed v and it goes up the track some distance, let's say x, if you started at distance x and then let it go, the speed that it's going to have when it gets back to the starting point will be exactly the same as the speed required to get it there in the first place. So it shouldn't be a big surprise that what we ended up finding was in fact the escape speed. So go ahead and do that now, just for the satisfaction of getting the right answer. So we got the square root of g times the mass of Rotan divided by the radius of Rotan. And that should do it. So about 1,700 meters per second, or 17 kilometers per second. I bet that's what they have in the book. And I'll check that just to make sure it led you astray. That's not the right answer. Is this 93? Yes. So now I have to figure out what I did wrong. Let's see. 1/6 times 10 to the 6th. What did I do? I think I've plugged the right numbers in. Let's see. There's nothing wrong with the approach here. Oh, I forgot the 2 under there, didn't I? I forgot to put the 2 there. Duh. Well, that's like forgetting to multiply by the square root of 2. So if I do that, multiply by the square root of 2, there we go. That's the right answer. So that's about 24,000 meters per second, or 24 kilometers per second. Sorry about that. All right, there you go. There's that assignment.